how to look at this problem and how we might think about moving forward. So as an organizer myself, I can hardly thank the organizers for inviting me to speak. So what I really would like to do is thank you all for coming and making this into what's been a really exciting and productive week. So the outline of this, I think this is straightforward, why a better model of CCQE is desirable, just beyond why it's good to do the physics as right as you can. I want to say some words about the shortcomings of some of the present models and what that list is and the evidence for what those shortfalls might cause you. To my mind, the principal difficulty is just in how well we end up treating these correlated pairs. The treatment of what's in the mean field seems to me to be relatively straightforward. The real issue is what do these correlated pairs actually do? And as Ingo pointed out so clearly in his talk, they play a very big role even though they only represent something like 20% of the nucleons. So we'll want to deal with the wave function of the pair in its spin, isospin, and spatial distribution, current conservation, and the resulting two-body currents. I'll give an example of what I consider to be a better model. The better model is the work that Carlson and collaborators have done. It's extremely difficult to extend it into heavier nuclei. So you have to settle on some approximations to that better model and then seeing how it might be generalized. There are very universal features to nuclei. The nuclear density is basically constant, and what really changes for the most part once you get in above carbon is just the surface to volume ratio that is there. So why should we care about CCQE? Well, the experiments looking at neutrino oscillations employ this interaction, and somewhere between 300 MeV and 3 GeV, it's a dominant, though not necessarily the most dominant reaction, especially at the highest energies. The problem is years ago, it was assumed to be readily calculable, experimentally identifiable, and allows you to assign the incident neutrino energy. And those, of course, once you've established what the flavor of the neutrino is, that's really all you need to know is for studying the oscillations, is assigning the energy. So there have been some 50 calculations published. I think this is something a slide I put together a year ago. I'm sure that number should be 60, and they're still coming. I mean, these papers just keep flooding in. I don't know whether that's the good news or the bad news. When a problem's solved, the publications sort of die off. And of course, it's really extremely relevant for neutrino oscillations. The oscillation parameter, as you know, is L over E. And if you're doing something like a long baseline experiment where delta m squared in 2,3 is 10 to the minus 3, and you're the order of 1,000 kilometers away, you're looking at 1 GeV type neutrinos. In the short baseline game, where some people believe there are sterile neutrinos with a mass the order of an electron volt, again, you're the order of 1 kilometer away, and again, the relevant energy that you have to deal with is a GeV. So this particular regime, which is difficult, turns out to be extremely important. Now, To my mind, there are many shortcomings in the present state of affairs. So many of the event generators in this regime are inadequate in that they simply have mean fields and they use impulse approximations for the interaction. Some of the worst apply 40-year-old nuclear physics, produce wrong cross-sections, assign incorrect incident energies, and possibly seriously affecting oscillation parameters. I find it disturbing that nucleon-nucleon interactions are not really manifestly present in these models, even though one is dealing with nuclei. So we know.
Are you talking about in a ground state or in a final state interaction?
Everywhere. The nucleon-nucleon interaction is relevant at both of those. When you're dealing with two-particle correlations and you're scattering off that two-particle correlation, it's very useful to know what the final state is. And it's a two-particle state. So you need the nucleon-nucleon interaction. You can't get away from it. And I think you'll see that in some of the things I'll show you. By the way, nothing that I show you is original. I have borrowed mercilessly from work that other people in this field have done. I simply got into it because I was, and still am, a member of the Mini-Boon collaboration and lived for, I don't know how long it was, Sam, 5 years? With the X factor. And trying to understand that became maybe somewhat of an obsession for me.
Interrupt you. These nucleon interactions are present, for example, in this type of models that Marco Martini showed yesterday. I mean, there is an explicit interaction in there.
Yes, it gets put in. So let's let that go. I mean, I think obviously if you make two-particle, two-hole states, something did it. But I'd like to know that that nucleon-nucleon interaction was, really tied back to what one thinks the nucleon-nucleon interaction is. So once you have these interactions present, then you have to deal with the issue of current conservation, both in the vector current and use PCAC in the axial current. And that gives rise to two-body currents, and they have a very important role in enhancing the cross-section. You have to respect that. And hadronic states in nuclei are not plane waves. That's, I think, a thing that one really has to pay attention to. And the physics, I think, to improve the modeling of neutrino nucleus is in hand. Maybe a little further than just outside this room, but it's somewhere around. So that for A less than 12, thanks to Monte Carlo Green's function techniques, you can get a full nuclear wave function, both in the initial state and, if you like, in the final state. It's unfortunately non-relativistic, but it does give you Q and omega, the quantities that you really need to understand.
I don't understand the remark. Q and omega relate to scattering parameters external to the nuclear wave function. So what do you mean?
So I mean, when you do a scattering process, say with either electrons or neutrinos, you generate a Q and omega associated with that interaction. It comes from that formulation. Okay? I mean, in cases where you have, for example, just a momentum distribution, you need a spectral function. The spectral function helps you get the energy, but you don't really know, in my mind, what that yield actually is. So I think only for A less than 12 do you have a theory, albeit non-relativistic, that gives you what you really need to deal with the problem.
What you mean is that given the full nuclear wave function and knowledge of the interaction, you can calculate
Q and omega, yes.
We know Q and omega from the lepton.
No, you don't. Not if you're dealing with neutrinos.
No, but electron scattering.
Oh, and electron scattering, you do.
Or under the integral over the neutrino flux. But for a nuclear theorist, you know Q and omega. It's really how does the nucleus respond at that value of Q and omega. I would say it that way.
Okay, well,
Whatever. It's not
thank you, I think. However, there are certain universalities that are observed, and I think thanks to what Bill commented yesterday, it looks like Kusel relativistic effects can be added in and considerably moving up in energy and momentum where one could implement these things that appear to be non-relativistic. Hadronic currents satisfying PCAC and CVC demand that you have two-body currents that affect both the Q and omega response. And this turns out to be especially important in the transverse sector. The quantitative evaluation of that really requires two-body wave functions, not just plain waves. So I think the free nucleon form factors are not really an issue at this point. They may become at some time when we are doing much finer experiments, but at the present moment, my guess is that the form factors that we're using for free nucleons are just fine. Should you incorporate into that form factor nuclear effects? I think not. And of course, this is really directed at the experimentalists. If you're going to really break your heart trying to get some really good cross sections, you really need to know the flux comparably well. So if you're beating on your theoretical friends to get expressions for cross sections that are good to a few percent, then you have to get the flux to that comparable precision if you want to do that. Of course, in an oscillation experiment where you're using two detectors, that can be relaxed somewhat, unless you're looking for subtle effects like Debbie mentioned earlier of well, anyway, senior moment. And then suppose you do have a good description of the neutrino nucleus charge current interaction and quasi-elastic. How do you actually deal with final state interactions if you're really interested in that? And of course, people who you want to use liquid argon as a detector really do want to have as much information about the final state as they believe they can extract from their detector. So how bad is what we do? This is a worst case scenario, but there is the Fermi gas as a momentum distribution for oxygen-16 versus some work that was done by Cioffi Degliati and collaborators. And you see that Fermi gas is a pretty poor approximation to what the momentum distribution actually is. And actually, it's even worse than it looks, because you should multiply that momentum distribution by k squared dk. Bill Donnelly told me there's some subtle modifications to that. But nevertheless, if you just take that picture at face value, the higher momenta are weighted with the square of that momentum.
Yeah, but still, I think one has to say also that large parts of this plot are not always accessible in normal reactions, let's say, like that, okay?
Yeah, you bet. You bet.
Very much depending on the kinematical situation.
Yeah. Well, unfortunately for those of us in the mini Boone experiment and T2K, we certainly are dealing out to here.
On some level, it doesn't look horrible, but if you put that on a linear scale and look at the low momentum part, like changing your cross section by factors of 2.
Yeah, no, I understand. There isn't much of it, but it has a big impact on the cross section, and Ulrich knows this. He just wants to be heard, I think.
You know what I'm saying? What I'm saying is that long tail that everybody likes to plot nowadays, that is sort of irrelevant. What's more relevant is indeed the depletion at the lower side. That indeed makes it.
I think they're both relevant, and you should be careful. This is a probability, and cross sections depend on amplitude, and that 20% gets quite a bit bigger if you take an amplitude.
Thank you, Joe. Is it really so? Yes. These are some inclusive momentum distributions for the deuteron, helium-3, helium-4, so on and so forth, out through nuclear matter. So that high momentum tail is certainly there, and experiments like Doug told us about earlier in the week actually give you some details about what the structure of that high momentum component is. The high momentum component comes from considering the nucleon interaction. Here's a mean field wave function as a function of distance, and here is a two-body wave function between a proton and a neutron in the nucleus, and this extraordinary curvature that occurs at a Fermi and inside is what gives rise to the high momentum components. So if you want to get the high momentum components, it seems to me there's no way that you can get at it unless you put in a nucleon-nucleon interaction. And if you look here, this is from a paper on the still on the archive from Cioffi Degliotti, showing the two-body correlations Pn and twice the pp distribution. That's this. This is separately broken into pp and pn below. And you notice there's a really universal behavior, more or less, to that two-body structure. Understanding how that particular pp and pn distribution gives rise to the kind of thing that Doug sees from the Cioffi Degliotti paper, I think will take some work, but I'm sure it can be done. Yes?
I just had a question that, that again, not a nuclear theorist, that body density, how is that defined? In any of the terms in that expression?
The two-body wave function?
No, the densities that are in the equation you have to know about.
Ooh.
Two-body wave function, sure.
Yeah, you just
Take
take.
the matrix element, the delta of r minus r sub I times delta of r prime minus r sub j, summed on I and j, and take the matrix element.
Yeah.
Generalization of the usual one-body density.
So what's the impact of those pair correlations? Well, this was the original mini Boone data. And those lines that you see there were a consensus of theory previous to our doing our experiment. That, I should say again, we called it quasi-elastic. What it actually was neutrino scattering on carbon, where we observed a muon and no pions. Not exactly clear that that's the same definition that those calculating quasi-elastic scattering were using. They, for the most part, were using the definition of the scattering that actually comes from the mean field. So just looking at the things that were basically the order of 3q squared over 2m, centered about that.
But you see, even in that theory consensus, there's quite a spread of terms. So
We could live with that if that were the truth.
Well,
So-
I mean, we could live with that. I mean, Huber et al., they say that the optimistic uncertainties that we need on cross-section times efficiency is like 10%, and I see 10% spreads there.
Yeah, it might be the order of plus or minus 5%, if you call 10. So Mini Boone fitted the in a way that I think that Rex Taylor and Tippy Katori were rather ingenious in finding such a good fit, albeit abusing the axial mass by increasing it to 1.35 GeV. It really fit the data as well as anything that I've seen. Now, there was there's Marco. Yes. Martini and collaborators came out with a paper in 2009 that just ran their data point, their theory, right through the Mini Boone data using a proper value of m sub a. And what they introduced was, I think, the right physics. They put in n particle n holes. They suggested that this was really, for the most part, due to the pion and the tensor interaction. I think that's absolutely correct. I have a confession to make in the way I set back this field. If you look at this paper, which I think was coming from probably the PhD thesis of Marteau, this was in 1999, and it absolutely, I mean, I think the data is very similar. Some of the details in the calculation were incorrect. What they were doing was calculating what you would see in a water Cherenkov counter and would call quasi-elastic scattering, because you'd pretty much be stuck with the same definition that Mini Boone had to use. And they had that cross-section exactly right. The problem was, if you do the free nucleon cross-section, it comes up in here somewhere. And I wrote them a rather rude email asking them, how can you get a quasi-elastic cross-section that's larger than the free nucleon? Because you see, all the theory predictions at the time were below that. But they understood the limitations of the measurement that we were doing, and properly included the two-particle, two-hole contributions, and had pretty much the right cross-section. So I set back the field by a decade at that time, and I'll try not to do that today. And there are just some of the diagrams. Now, if you look at the theory that they came up with, you do have a penalty you have to pay. If you get this enhancement, it's going to cost you some uncertainty, actually, in how much energy you gave up in the collision, and just using a simple Fermi gas model to approximate the energy is clearly incorrect. So just to say a word about that theory, and it was one of the things that troubled me greatly at the time, and still troubles me, but somewhat less, is you'll notice that the magnetic, the transverse magnetic and the axial form factor get exactly the same enhancement. So similarly, exactly that term also appears in the interference term. So that's one reason the cross-section got large, in that model. You enhanced the magnetic piece, you enhanced the axial piece. They both got enhanced, and they also, because what we were looking at the time was the constructive interference in neutrino scattering, really gave quite a boost to the cross-section. Now, that group went ahead, along with others, and looked at what was the effect on the energy that you would infer. So this is, you're looking now with a mini Boone flux. You see a 350 MeV muon, and these are different angles that you would see it at. This is the central value that you would get in scattering off a nucleon at rest. This spread here is the simple spread that you would get from just a mean field approximation, and the n particle n hole piece gives you this very long tail out here in energy that the incident neutrino could have had in their model. And similarly, you see it for a variety of energies there. I want to show you in this next slide the impact that could have on an oscillation experiment. This is the electron-neutrino excess seen by mini Boone. That's this green, the data here shown in green. If you then try to, say, fit that and assign the energies just using a straight quasi-elastic with just say a straight Fermi gas or a mean field, this line here represents that dotted line. What you get if you assume that it doesn't come from n particle n hole. And when you include the contributions of n particle n hole, that distribution in neutrino energy shifts as shown in the red line. Now, in our first publication from mini Boone, the paucity of events in this region here was taken as strict evidence that there was strong disagreement with the LSND experiment. This removes some of that, certainly not entirely, but I just simply show it as a caution for what one should do in understanding clearly when you're assigning neutrino energies that you do the best job you can. I would say that most of what I have to say today doesn't give you great comfort in the sense that what it does is it just makes your assignment of neutrino energy more uncertain. Pardon me?
I'm confused because you have a low energy tail from this, and how come you're getting into a higher energy?
Oh, the higher energy comes because you made the assignment of the neutrino energy from using straight Fermi gas.
No, but it has a low energy tail, so the mu energy is lower, angle is the same, so you get a low energy, not a high energy.
You get a higher energy. Ulrich, tell him that this result is robust.
Ari, there are so many, from different groups, there are so many researchers around on that, and they are all published. So go ahead and read this stuff. And then
Well,
you'll
simple
find
fraction, go left to the right.
Yeah, I mean, there's no question that it increases the neutrino energy because you are giving up more energy than you thought you were in a simple Fermi gas. That's simple. it has a significant impact on the assignment, and as Ulrich says, this result is robust. Now, robust, I believe it's certainly qualitatively robust. That is, it gives rise to an increase in the assigned neutrino energy. The issue is quantitatively just how large is that shift, and how would we go about proving it if it turned out to be a crucial matter in understanding neutrino oscillations.
So
Yes?
Before you go on, though.
Sure, please.
I'm
Shall I go back?
Yes. I'm still struggling to reconcile these sorts of plots with what was shown yesterday, where the inclusion of these sorts of effects in the mini-moon spectrum really didn't change the oscillation results.
Oh, one reason for that was that the errors here are really quite large. Okay? The statistical uncertainties out here make this fit and that fit not really awfully different, just for statistical reasons.
Okay.
Okay?
So the point then is this effect isn't important, right? It's not
No?
less important than the statistical errors on your measurement.
Oh, you bet. So
Right.
we're thinking about doing good measurements.
Sure. So,
Yeah.
but it's not driving, the uncertainties. This effect.
Oh.
Right? Like you're better off in some senses with more data rather than better theory.
No, I would say that it's the inverse
No.
issue. It's
More
that
data necessitates better
as we
models.
get to more and more data, we start to then have this as an inherent barrier to
Yeah.
our analysis, because we don't know if it's there or not, or how big it should be, right? It's right now, it's hidden under.
I mean, the other thing, right, there's at least one person in the audience and perhaps the speaker who found the whole chain of argument less than convincing. Right?
Okay.
Because it wasn't clear what was actually included in the analysis. And when there are a lot of backgrounds, that becomes a
You bet.
problem potentially. So it wasn't clear the background for the
That's something the mini-boom people should sort out.
Yes,
among
it's
themselves.
something I think the mini-moon people should sort out, because probably it's correct, right, that it's not their driving systematic for exactly the reason Gerry says, but
Yeah.
it'd be nice to see a more convincing demonstration.
Okay. So I was looking around trying to convince myself, do I understand these alleged effects of n particle n whole, and their impact on the spectrum? Were they all correct? And I had the good fortune to come across a paper, a review paper written by Benhar, Day, and Ingo. That in the course of reading that paper referred me to this paper by Joe Carlson, Rocco Schiavillo, Jordan, and Ingo. So he plays a big role in this game, actually. So well, I'll just give the whole story. Joe really, I think, modestly refrained from showing you what a really terrific piece of work this was. So what they were doing was looking at the longitudinal and transverse scattering from helium-3 and helium-4 with electrons in quasi-elastic scattering. So here I've shown the longitudinal piece here, which dominates here, shrinks, and the transverse piece begins to dominate over the longitudinal piece once you get out to momentum transfers of 500 MeV over C. That's what was observed in helium-3. If you go to helium-4, which is a much denser nucleus, things are more tightly bound, you'll notice the picture is in some ways similar. This is the longitudinal and transverse piece overlapping here. And then as the momentum transfer increases, the dominance of the transverse piece relative to the longitudinal piece is greatly enhanced. So
So
Yes?
Is this quasi-elastic because this is the full response?
I'm sorry, I didn't.
Say this is quasi-elastic. There's the quasi-elastic peak there, but there's also the inelastic part of the cross-section.
Well, I think, a certain cutoff is made, albeit arbitrary, but that's what was designed. I think in the paper they tell you particular values that they assign for where they cut this off. Pardon me.
This is data, right?
This is data.
Okay. Which contain quasi-elastic and inelastic.
Yes. Oh, yes. But I mean, that's really, I would love to have data like that to deal with. So if you now convert that via scaling response functions, there's helium-3 as a function of the scaling variable psi prime, which is basically y divided by the Fermi momentum, so that you can make comparable comparisons between different nuclei. And there, again, you see the effect, really the longitudinal piece in green, the transverse in orange. And in each case, you're taking out basically the charge in the case of the longitudinal piece and the magnetic moments and trivial kinematic dependence in the magnetic form factor, so that they, in a relativistic Fermi gas, these two things should have been equal. Okay? Clearly something's going on in that transverse sector. So these guys actually went ahead and computed a thing called the Euclidean response. I think Joe treated that in sufficient detail. And they just actually go ahead, compute the currents. In the case I've written it there for just the transverse current, you subtract any contribution that just simply is due to the scattering of deuterium, and are left then with this expression for the quasi-elastic scattering of the nucleons in helium-3 and helium-4. They include two-body currents. They're, just simply obtained by using the continuity equation. Here the interaction is just electromagnetic, so you're just dealing with the current. The currents are a one and two body piece. The one body piece comes from commuting the charge component of the current with the kinetic energy. The two body pieces come from basically commuting that current with the two body potential.
Gerry, just a technical comment.
Yeah.
That actually doesn't give you the two-body curve. It gives you the divergence of it. Any piece that goes like a curl is greater than that last equation. And curl pieces are non-trivial. They actually are important.
Okay. Presumably they did it right.
You actually can't really
Yeah.
do this. You
But-
do what you can do, but you can't
Yeah,
do
but
it all.
But then you adjust those pieces to some data, right?
That's where you start playing games. So you do what you can do.
well, no, I understand. But what did Joe say?
It said that, obviously you do have model dependence, particularly in the currents not constrained by the continuity equation. But you do, what's typically done is to adjust those currents. You have some model for those currents which is reasonable, and then you fit it to some data, and then you use that.
Uh-huh.
You fit it to nothing to do with quasi-elasticity.
So it comes from, it's independent of quasi-elastic scattering, is what you're saying. Yeah. And here is just one of the explicit expressions, which I think is not useful for us to go into at this point. But at any rate, here is Euclidean longitudinal response for helium-4 at different momentum transfers, 300 MeV, 400 MeV, 500, and 600 MeV. The basically one-body current is here in orange. This is the two-body, including the two-body piece, basically shows up in this light blue that you can't see. And you'll notice it's also invisible here because it basically lies on top of the one-body piece. So the two-body effects hardly affect at all the longitudinal response.
That's a two-body current. I mean, the two-body final state interactions and the charge exchange, whatever, are all in all of those currents. So you have to be a little bit careful.
Okay.
Did the experiment measure the Euclidean response?
No, there's a transformation involved.
You could do an integral.
Integrate all of the data. Integrate
Yeah.
the data.
Yeah. I'm sure Ingo kept them honest. So if you now go and look at the transverse response, you find it's a very different story. Here is what you get with a one-body current, and here is these blue points, the inclusion of a two-body response. It seems to greatly enhance that cross-section. In some cases, the order of 50%. Or more. And that, if I understand this properly, this is just the result of just doing the calculation. There's no fitting involved. You just go in and run the calculation, and this is what comes out. So it's not a fitting job. Just blown up somewhat more so that you can see it. This is at 300 MeV over 3 momentum, 300 MeV over C going here. This tau is basically looking at the inverse of the energy that you carried out the integration over. So this is points above 100 MeV. In final state energy. So one thing that apparently is relatively straightforward for them to calculate is a sum rule, in which you just take and integrate that result through to basically infinite energy. So here's what happens in the case of the longitudinal piece. The sum rule in this case should work to give you 1. You notice that the result is relatively close to 1, especially at higher momentum. The really surprising thing is when you just put in the numbers for the transverse piece, you'll notice that the increase is the order of 50 to 60% in terms of the integrated cross-section going out to all energy for different values of the 3 momentum transfer. So here you see an enormous enhancement, and for a while I thought that was the whole story, and I could not understand why Martini and company had an enhanced axial piece. So I was pushing for a while, it's all in the transverse magnetic sector. But I think these calculations that Carlson and company have been carrying out is showing an enhancement in the axial sector, and we'll have a chance to see that at the end of this talk.
Can I ask just a minor question?
Sure.
about Steric's numbers? So is there a logical explanation for why when you consider 1 and 2 body current operators in the longitudinal plate piece, it goes down instead of up? Or that there's, that all those numbers when you have 1 plus 2, they're all lower in that column than in that column. Is it just that?
Slight suppression in the longitude.
Would some theorists like to answer that?
It's not required to go up.
It's not required, okay.
Yeah.
So it could have been that there would be interference in the transverse as well, and it might have gone, might not have gone up.
So that's clearly very important. Now, that paper that I referred to is really worth reading because there's a lot of things in there that they did to try to understand what was going on. And for me, one of the most interesting things was if you use a plane wave initial and final state, and what's shown here is the excess longitudinal and transverse strength that comes from terms including two-body currents, where now the initial and final hadronic states are plane waves. Look at how small that enhancement is. It's 10% or less, whereas what we were seeing before was 50 and 60%. So there's a serious lesson there that one has to really beware of plane waves in computing these things. And so you just don't get adequate enhancement if you have plane waves. So I would say, God, that was potentially really bad news. Here's a quote from the paper. It's now clear that this enhancement arises from the concerted interplay of tensor interactions, correlations both in the ground and scattering states, a successful prediction of longitudinal and transverse response functions in the quasi-elastic region demands an accurate description of nuclear dynamics based on realistic interactions and currents. Oh. That's really bad news. If true, do we have to do a Green's function Monte Carlo for every nucleus? That'd be terrible.
Not every nucleus, just argon, oxygen. Just those three.
So, I think that's impossible. So, how do we get all of this complexity into an event generator? Well, is my belief and even more fervent hope that we don't have to. I'm sorry if you have trouble reading this, but the universality of nucleon-nucleon short-range correlations and nucleon momentum distributions. Oh, so that sounds like it might be a place. Might be a place to start. So maybe this stuff you only have to do in 1 or 2 cases, and you would understand how to transport it from one nucleus to another. So here is this paper by Cioffi, Degliotti, and collaborators that came out in PhysRev this year. What you have here is the momentum distributions as a function of the momentum in inverse Fermis. And here's the deuteron, helium-3, helium-4, oxygen-16, and calcium-40. And once you get out to oxygen-16 and calcium-40, they almost lie on top of one another. Certainly the tails are really similar, and that seems reasonable. If the tail is due to the two-body interaction, presumably it is not all that worrisome about the environment it finds itself in. It's the two-body interaction at short distances. And this is the varying amounts of it as shown in a blown-up scale out at high momentum transfer for the deuteron up through calcium-40. That's as far as they carried out that calculation.
Do they say anything about extrapolating the higher 8 and 40? Or is it just 40 was the highest number they calculated?
Well, they seem to, for whatever reason, stay with self-conjugate nuclei. That is, n equals z, and calcium-40 is the heaviest one you got. So I think that is not a serious limitation. But those are some of the things we'll have to be looking at. Okay.
Comment. Phenomenologically, you can basically take that kind of picture and build it out as far as we've taken data. Whether or not it's valid.
Well, no, but I mean, we do have some data on iron and lead, for example.
So do we. So basically, if you look at what Claudio does, you take the ratio of those.
Did you want me to show something?
Go back one.
Go back.
Look at the bottom left figure. Those functional forms are all the same.
Yeah.
All right. So in this high X data, all we ever really argue is that what we observe are functional forms that are the same. We measure a constant that's independent of Q squared or a Lessler. So as long as we're proportional to what he's getting there, and we make measurements on all these nuclei, and that's where that holds together, it's proportional. You can play a phenomenological game of, oh, I know the high momentum tail for this nucleus, and then can make sure my integral is correct, so I get the low momentum piece normalized properly.
Doing okay?
Beautifully for mean field. So you can play a phenomenological game, which is fun for an event generator, which is why we are doing it. So whether or not it's perfect,
Well, it's wrong because, as I showed, the Heimann is tail at large X is measuring final state interaction. It doesn't measure initial momentum distribution.
so my point is just if I take the ratio of what is there and the ratio of the data, it's proportional. It comes out the same. So right or wrong, it seems to work. So phenomenologically, for whatever reason, and I don't disagree. That's certainly what Inga says is not incorrect, but it seems to work. I will not claim to know why.
Okay, so can I also make a comment
Sure.
from a theoretical side? I mean, you pointed out that all these slopes there are very similar in the I region, and I think this is quite easy to understand. It's mainly really a phase space argument, you know? And there are, I must say, outsiders in this community, namely we, but also the group in Valencia, Rosette, and his people. I think Luis worked on that once. We can actually generate these high momentum tails in transport, you know, by making a very simple-minded ansatz for the force. It's very much independent of the particular interaction. The main thing is the phase space that you have available in nuclear matter for scattering into, and that determines the slope there. The absolute height depends somewhat on the interaction, of course, but the slope is determined quite well from quite general arguments.
Okay.
I don't believe that to be true. We've done calculations without ion exchange, and they look very different.
Well, I can show you things like that, and there's, as I said, this is an outsider's opinion. We did that, but we're in good company. The people in Valencia also came out with the very same result, and it works very well.
So what is the weight?
Generate spectral functions as good as Ben Haas, essentially where you need one parameter, sort of average nucleon interaction, nothing more. You don't have to know anything fancy about the interaction whatsoever. You just need to know the average number, one number.
But let me make a comment.
Sure.
I think what Ingo was saying is correct, is that the shape of the quasi-elastic peak has also a final state interaction component.
Sure.
And there's nothing you can do here that's going to predict it. So if you just use this, you're going to be missing the tail of the quasi-elastic peak that you see inside scaling. So you can do all you want, but at the end, you have to do something else too.
Now, why do you believe that the final state interactions are not in this?
Because
Or, I mean, but if I use a nucleon interaction consistently, I'll have the final state interaction in. No?
I use that spectral function.
No.
Okay, and I compare the quasi-elastic peak to size scaling, and it doesn't work.
Uh-huh, okay.
And I asked, why doesn't it work? And Ingo told me, because it's not supposed to work. It's because I'm using the final state interaction. But I know it doesn't work.
Okay.
Right. So the idea is, okay, you can make those momentum distributions for any nucleus following the phonological procedure, which is from data. Then you also need to include the final state interactions if you want to properly calculate the cross section. That would be the whole. Yes, you have to put all these pieces together.
Right.
And
Okay,
it's
so
a
now then-
non-logical trick, and why is it working back then?
Okay. Oh,
Do you mind if I add one other thing that I think might be interesting from a generator perspective?
sure.
So one question I've had though is, how far out is important to get this tail in the generator? So like where, I think we saw hints of that yesterday with what someone showed that isn't in the plots that I've seen, but it'd be nice to see, as using one of these theoretical models, slicing up in K and seeing how much it actually contributes when you integrate across the Minerva flux, when you integrate across the TDK
So
flux.
I think there was some contribution yesterday that sort of addressed that issue. I cannot recall what its content was, but it certainly showed that you didn't need, you don't need to go out all that far. The Q and omega that you need. Bill?
I mean, this is exactly the point that puzzles me in a lot of this. If you took this and you did something, even if it's not right, like plane wave impulse approximation, this is an approximation for the spectral function,
Please
which
talk
is
one
not
at a
good.
time, I'm sorry. Laura.
Ulrich?
Yeah.
Thanks.
For cross purposes, if you took this to PWIA, use this as an approximation for the spectral function, you would just simply do an integral KdK of this level, and that would supposedly give you the scaling function. And everything you're pointing to, K greater than 1.5, is a few percent of the cross section. In other words, I'm puzzled by this focus on this high K tail. This is not where most of the cross section comes from. It is when you do E prime
Sure.
2P and you go into that region and
Uh-huh.
study it. But if you're doing neutrino muon, 90-something% is coming from below 1 in this.
But the correlation,
Correct. It's all about getting that low momentum normalization factor. Mean field will not get absolute cross.
And that's all I'm saying. By focusing out there on what the tail is doing is not the point.
Okay.
It's normalization at the low region.
but the correlation does go into low momentum.
It's normalized.
Yeah,
That's
yeah,
what you're saying. But
yeah.
That's unitary.
Okay.
Of course you have to do that.
Yeah.
But I'm saying the shape inside is what determines your
See.
quasi-elastic cross-section,
But you-
not what the tail is doing.
It's not just the cross section, right? You need to have the dynamical mechanisms modeled correctly, otherwise you don't reliably reconstruct neutrino energy from the lepton.
But you see that,
It's
no,
the
no,
second
no, no,
thing.
but hold on. No, hold
Here
on.
we go.
Let me answer that.
We have one at a time.
No, let
Wait,
me
wait, wait.
address that if I can. I mean, I haven't quite finished, that was the problem. You see, I think this is the distinction though. If it is inclusive, it's one thing. But if it's not, if you actually are detecting hadrons, then it's a different story. Because you're asking a different question. I know I keep saying that over and over again, but I truly believe this is a big issue as to what goes into the modeling and what details need for your neutrino experiments. I'll shut up at this point.
You missed my point. My point has to do with the lepton kinematics and not talking about it protecting the hadron system. Right. You need to model, it's not just the total cross section, you need to model the lepton kinematics correctly, right? In order to reconstruct the neutrino energy properly, or at least understand how poorly you're doing it, right? And to do that, you have to understand features of that tail.
I don't think so at
I
all.
don't think so
Because
either.
the weight is so small.
Excuse me.
Totally go with Bill. Yeah,
Look at this, we actually agree here.
Okay.
I really missed my point.
Get Joe.
Ingo and then Joe.
Totally.
Wait, Ingo and then Joe, please.
This tail does indeed have low probability. As I pointed out, these correlated nucleons are responsible for 20% of the probability, maybe 50% for average quantities like removal energies and kinetic energies. This will certainly to some degree affect the reconstruction of the incoming neutrino energy. But this is not, I think, the major point. The major point which Gerry was making was, once you have these correlations in the wave function, then the two-body processes enhance the cross-section by an awful lot, like 50% for the transverse. And so you cannot say it is this tail which enhances the cross-section. It is the correlations which are responsible for, on the one hand side, this tail, on the other side, the enhancement of the cross-section via the MEC. This is the big effect.
Joe, did you have a comment?
That was basically the same as what he did.
Okay. Yeah, all right. Okay. So this is some more from that paper of Cioffi Degliotti. And I just wanted to point out that once you get up to say something like oxygen, going from oxygen to calcium, you can see that the fraction P1 is basically the part associated with, if you like, the correlated part, the two-body part. That 20% number is really quite a good number in terms of talking about the universality of this particular effect. So the thing that I'm finding trouble in understanding in the Cioffi Degliotti paper is in that paper they now give you the pairs in terms of their spin and their isospin. And of course our favorite correlation is the deuteron with s equals 1 and t equals 0, and one expects from work of the kind that Doug has done that should be at high momentum the really dominant piece. And yet in the Cioffi Degliotti paper, by the time you're at 016, notice that the s equals 1, t equals 1 part contributes a higher fraction of the high momentum than does the correlated deuteron piece. So I don't really know how to work that out. If you look at a table in that paper, here they're listing numerically what the piece in that what they call a short-range correlation. I think it's best to just refer to it as a correlated pair. There's an independent particle model where you just simply combine by straight combinatorics the S and T of the pairs that are involved. And you'll notice that in their work anyway, the final state is not really all that different from the what you get from just assigning S and T from an independent particle model. And you'll notice that as you go to bigger and bigger nuclei, the contribution of that S equals 1, T equals 1 pair gets larger and larger. It's now clearly dominant over what you would get in terms of the number of NP pairs.
I think this is somewhat misleading.
I know, I'm headed there. So in T equals 1, you have NN, NP, and PP pairs. The tensor interaction requires S equals 1. And so if you have S equals 1 and T equals 1, the spatial wave function of those pairs has to be antisymmetric under exchange. And for a while, I thought that that was one of the things that was possibly quenching their contribution when you were looking at higher momentum transfer. I don't know whether that turns out to be true or not. If you just did a simple reckoning of NP, and you'd have to count twice the PP pairs because you could see either proton when you're doing that. The ratio is just 1.2, whereas in fact what Doug sees is the order of 10. Now, Joe.
You have to be careful with what operators and what momentum distributions people are calculating. If you concentrate on zero total momentum pairs, you get a very different answer than if you integrate over the center of mass of all pairs. The latter is dominated by just counting arguments like Choppy has, but the former is not.
Yeah.
And that's basically requiring that the pair is close together spatially.
Yes. So this is just showing what Doug showed us earlier in the week, basically of the relative to E prime P, the E prime 2P that they measured was basically 10% of that total amount. What they saw was basically back-to-back pairs, and the question, which I think is really reasonable, quite reasonable, is this certainly measures the back-to-back pairs, but there's a much larger total phase space that you might be able to look at, and perhaps the class spectrometer at JLab is a natural place to go looking for some of that data. Notice this is just a very simple energy that you might assign to these pairs from something like a Fermi gas model. But look at this extraordinary high energy contribution from those correlated pairs. Yes? I have trouble hearing.
I wanted to make sure that I understood Joe's comment. Again, I'm thinking about how this is going to generator. So if you're scattering off pairs that are not back to back, the probability should come from that plot we saw previously.
Well, the pairs that can get a contribution from two body currents have to be close together because they have to be,
You have to be able to hit them.
So basically, this thing is dominated by pairs that are close together, which tend to be back to back. But if you calculate randomly the distribution function of two nucleons, they can come from different parts of the nucleus and add up to give a random total momentum. And so those aren't going to participate in the two-body process.
Yes. Sam, I think.
As far as the event generator, but people now looking at the class data, you just take a quasi-neutron and then move it with Fermi motion, you can easily model what you observe in the data. So it's fairly easy to build an event generator that looks like the data.
So, how do we get there? How do we get there from here? So this is the universal model for CCQE. So, so obviously, I think we have to use a rather simplified nucleon-nucleon interaction to get that momentum distribution at least approximately correctly. So 80% of the nucleons are in a mean field, and they can be calculated, their response can be calculated via relatively standard prescriptions with a neutrino flux provided. Now, to me, the whole problem comes in this issue of dealing with the correlated pairs. They're really important. They're apparently tricky to calculate, as I'm hearing. So I'm totally supportive of turning that part of the job over to experts and have them calculate what the short range, those two-body currents are with short range correlations. And I hope that the results that are obtainable are sufficiently general that you can add them to the mean field results. And the value of both the 3 momentum transfer and omega should basically come out of such calculation. So in this case, we're trying to separate the problem into a calculation from a piece due to the mean field to a piece that's really tricky, and it's tricky but hopefully sufficiently universal that you don't have to make great changes in it as you go from nucleus to nucleus. Yes?
Just one little add-on. When trying to get spectral functions and momentum distributions for the heavy nuclei where we don't have exact calculations. We have tried to do that using local density approximation for the correlated piece.
Yes.
And for the momentum distribution, that it could be verified that this LDA for the correlated piece was an excellent approximation. This might be added in a sense to your third point there.
Okay. Thank you. Let me just flash I think there's one more bullet. I just want to say, while it's more complicated than what we presently do, it seems to me it's apt to provide us more solid base for us to build on, to move and absorb improvements and discoveries as they're made. Excuse me. Bill?
I mean, just to emphasize what I said in the first day, these definitions you're looking for, you do realize that the 80-20 is model dependent.
Pardon me?
That the 80%, 20% is model dependent.
Sure.
It depends on which mean field. And so, for example, if it is a relativistic mean field, that's not the breakdown.
You bet.
Because the correlations are
You have some correlations already. Yeah.
And it's a significant issue.
Sure.
Model to model as to where these correlations are.
Yeah.
But
So-
what's really great about this is that it's factorized, and in some sense, that's like if we have a framework to do this, then it should be easy to be able to incorporate that kind of uncertainty or toggle between them. I mean, again, you have to be consistent, but my point is that this is still a nice prescription for how to treat that at some point.
So I think the question to ask, Bill, if you did the relativistic mean field, would you know what piece to take out of the correlated pair in the other case?
Well, it's this question of consistency.
Yeah.
Handled on the same footing, and I'm not sure I do know that.
Okay. Joe?
I'm a little bit nervous about this separation because it's an inclusive process. You can have an amplitude on one side where the momentum is coming from an exchange current, on the other side where it's coming from the external momentum, and you can't. It's not just two cross sections that you're adding up.
No. Well, I certainly agree with that, and Joe, that's why we pay people like you. Well, not enough, but. Excuse me.
I don't know. Let me take some issue with this, okay? Let's just try to do something very simple. Let's calculate the longitudinal response function. All the two body counts don't contribute to longitudinal response functions, fine. So we try use a procedure, and we cannot using this procedure. You cannot reproduce the size scaling curve. You can't reproduce the longitudinal response function.
Oh, I think that's not correct. I mean, the asymmetry that you see, I take it in the longitudinal. That's what you're talking about. That came just naturally into what Carlson calculated.
But Gerry, in relativistic mean field theory, it would be 100%.
You get it all there. Yeah. No, I understand. Yeah, I know.
I mean, I don't know what a 20, so you subtract 20%, you gotta put it back into the longitudinal. I'm saying you can't take 20% and say, give it to this guy, and this guy gives you 0, and then you're left with 80%. You gotta, longitudinal includes everything.
Yes.
So I don't think you can separate this with a longitudinal part. Because the two-body currents are 0, but everything else.
So all you need, yeah. But if you use a one-body, the one-body current, you'll get 80. Let me exaggerate. 80% of it from the protons in the mean field, and then you'll get the other 20% from the high momentum protons that are in the correlated pair. So I don't see a problem.
That's wrong. That's just plain wrong. If your mean field is a relativistic mean
No, I understand.
That's what I'm trying to say, though, that it depends on your representation,
Yeah.
your mean field. In some, you get 100%
Yeah.
and 0. In others, you get 80,
Sure.
20. I mean,
So why do I have to use the relativistic mean field?
because it's good.
Thank you.
So we're talking about good and better, but what is good enough? That's the question.
Better than what we have now.
But is it good enough?
Well, I really couldn't answer that. I mean, certainly at the standards, I think that Debbie set that she wanted earlier in the week at a few percent. I certainly don't believe it would get there without some real tuning, and the question is whether you would end up really believing that tuning or not. I really couldn't say.
So let me put it a different way then.
Sure.
At what point would you say the model is good enough that I can relax a near detector constraint?
Oh.
Right? Imagine you have a horse race between a near detector and some models. You know, to me it looks like near detector is just winning.
Yeah, I would not argue with that.
I don't think this is a competition between you do one or the
Yeah.
other.
Yeah.
So all the TTK people are going to go,
This is a slightly different near detector. I mean, I'm just imagining that, you know, it looks like if I just built an enormous dictionary of data with my near detector and
Ooh.
really nailed down my flux, that this is going to put me ahead.
doesn't work, right?
Yeah.
Because you still have to be able to take an event and say what the true neutrino energy was. And
But-
you cannot do that with a near detector. You can do it with a monochromatic beam. We should go back to that one.
Sam, would you run this?
How many more slides do you have? Give me 10 more minutes.
Pardon me?
How many more slides do we have? 10 more?
I'm just. Wait just a second. Let me get to a couple of points here. So I'm not going to. I don't need to say any more about this. Yeah. Wait. So here's how you can do a better job on your flux. It takes a certain amount of courage, but here's how you do it. You basically build yourself a deuterium time projection chamber. It has to be the order of a cubic meter and have about 200 atmospheres of pressure in it. Now, safety people have problems with this, but let me assure you that the Department of Energy, or at least a piece of the Department of Energy, looked at this, because when Mr. Bodman was the secretary, they went crazy for hydrogen vehicles. And it turns out if you want to have a hydrogen car, you better have a high-pressure hydrogen container that doesn't weigh too much. Because if you basically took the fuel requirements and put it in the standard steel container, the container weighed 8 tons. So one had to find another solution to that problem, and fortunately it exists. It turns out that carbon composites basically are stronger than steel. Their density is the order of just slightly greater than 1. And so, you know, with a little courage, you could build such a detector. Now, the beauty of this is, of course, with a neutrino incident on a deuteron in the initial state, obviously the sum momentum of the neutron and proton is 0. And then you knock out a proton. So there are 2 protons in the final state. This is what came from a deuterium bubble chamber. These were the spectator particles that they observed. These very soft spectators were so soft that they couldn't see them in the liquid hydrogen. But you can see particles down to the order of 3 or 4 MeV of kinetic energy in this gaseous counter. The thing that's really lovely about it is by just detecting these 2 protons in the final state, you immediately have omega and Q. So if you're a real fuss budget and you worry about complications that come from high momentum components and things like that, you basically can select the events that have y less than 0. And so this is some fit to deuterium. I think it's clearly electron scattering data. But I think both the theory for what the cross-section in deuterium should be is probably good to 5%. And it would be a way of basically being able to measure the flux in a way that presumably could verify what comes out of your Monte Carlo calculation of the flux. I'm really concerned about just how well we know fluxes in these neutrino experiments. Yes?
You know, Minerva is even more pessimistic than this. We're basically saying the only way to do this is neutrino electron scattering.
Yeah. You need a lot of time, or an awful lot of neutrinos.
Or a lot of detector.
Or a lot of detector, yeah.
Can you drift in deuterium?
Pardon me?
Can you build a drift chamber in deuterium? You don't want a time projection chamber, you have to drift. Can you drift in deuterium?
Oh, yeah. Sure. Yeah, there's a chamber, a much smaller version of this that's being operated at SIN for basically capture. What are they looking for? I'm sorry, I don't remember the experiment right off. But a chamber very much like this has been built. It's much smaller.
Probably mu capture. It's probably mu capture.
Mu capture, yes. Yeah. Yes. Yeah. Yeah, Hugh.
I had one comment. Let's go back to the slide about the universal generator.
Woo. There?
Yeah, I wanted to emphasize one piece of this, which I think is absolutely vital, which is the idea that the calculations are now needing to be done offline by experts. You know, Monte Carlos need to be relatively fast, and you want the best physics. This is the only way to go. You know, we saw the first example of this in the talk that we heard about incorporating the Dieves model into yesterday. So we have a whole morning session about event generators. I hope we can come back and talk about this at a practical level and about some of the consistency questions.
For example, it's an absolute limit that it can't take more energy
Pardon?
to calculate the cross section than it does.
No, I just wanted one for Joe to show the axial thing. So if Joe, if Joe could come up here. I'm showing the slide that you showed yesterday and just went over very quickly and shows axial enhancement. I know you mailed it to me. I tried to find the axial enhancement on the next slide. would you please come up and make your point?
Let me just say here, I don't think you can make it very easily from that particular slide that I
Yeah,
showed.
okay.
I'm not quite sure what you wanted. But okay, so we've done calculations of some rules of neutral currents, and if you look in, for example, the transverse piece, which is common to neutrino and antineutrino, so not the interference, and you divide that into vector and axial vector. We don't find exactly the same enhancement in vector and axial vector, but we do find a substantial enhancement of order 50% in both. And in the interference, it's somewhat different, the vector enhancement as well. But basically,
Where do you get a q squared equal to 0?
q squared equals to 0. Yeah, I don't know. I'm not sure we calculated that, but we can.
Because we know it's 0, q squared equal to 0 from capture, from muon capture nuclei. There's no enhancement in the axial current at all. Q squared.
Okay, I'll be happy to discuss that with you and look at it.
Yeah, Joe, I did have this slide from you guys. Yeah, and here you can see it. Yeah, this is a calculation in lithium-6. This is the vector piece with one body, vector piece with two body. Here's the axial piece with one body, axial piece with two body. And so there is, she said, enhancement in both.
It may go to 0 at q squared equal to 0.
Pardon me?
It may go to 0 at q squared equal to 0.
Zero. Okay.
It's supposed to.
Okay.
Experimental.
That might be true, but it's not immediate.
I'm looking at the plot.
Aha.
Close to 1.
Yes.
I'm just saying that the two curves, the blue
Yeah.
one,
Yeah.
axial, seems to go to 1.
So I know this is the sum rule in carbon for one body and two body as a function of the three momentum transfer. And notice how large the enhancement is in that transverse magnetic piece. Yeah.
Okay, let's thank Gerry for his presentation.
Thank you all for your
We have a
indulgence.
coffee break starting at 10:30, and then we come back and have a whole hour reserved for discussion. So if there's any burning questions now, we can also come back after the coffee and have a more relaxed and caffeinated discussion. Is that okay? All right.
I don't like that idea of burning discussion.
No burning.
Burning issues, yes.
I thought that when you put it up, I was like, do we need an Ulrich Mosel? I was like, Unified generator? Ulrich Mosel generator?
Hi.
I just wanted to thank you for the propaganda you made for our Euclidean response paper.
Yes.
I think it was a very good
Is it not good? It's a great paper.
and has no echo whatsoever. You are, I think, the first guy who has read it.
Gee, I mean, I have read it and probably reread it 3 times now, just because every time you read it, you learn something more. It's a great paper.
I had lots of questions to Joe. That's why you see all these.
Oh, you bet. Various
Where you cut out this,
You
and
cut out that?
to get
Yes.
at the physics. What is playing
Yes.
a role? Nobody cares.
Oh, I could give a whole talk on just, stealing things from that paper. Thank you.
I really enjoyed your talk, Sharon.
Pardon me?
And I'm completely with you on page 26. We just have to find a way to get it to happen. I'm like, I don't care if the fraction changes. You can put that into the Monte Carlo. You could have bottle A and bottle B each with different toggles. It
Sure.
doesn't matter. But if you have a framework, you can do it.
Yeah,
And
that's
what
what.
we need is to
Yeah,
do it.
that's what I like about it. It's a physics framework.
Yes.
And the others have a lot of guesswork in it.
Yeah, no, we all hate them, and we're trying to change them. Like, and you've seen on TDK, we can do what you just said. We're doing it now.
Uh-huh.
We can. So let's do it.
Wonderful. Good.
Now we just need to get, just keep pushing.
Good.
I had a question about way back on the mini boon.
Sure. You want me to go back?
Yeah.
Okay. Oh boy. Well, why don't I do it in a more sensible way? Oh God. So swap displays. That's what we'll do. Okay. Let's get out of this damn thing. Let's see where we are here. There we are.
So the oscillation plot that you showed,
The next one. The next one.
Yeah,
You
the
betcha.
excess and the oscillation.
You betcha. There we go.
So the data points on here are reconstructed energy or corrected?
They are reconstructed energy just using Fermi gas, and which is the same thing as quasi-elastic with no particle, no hole.
Okay.
Then,
But these lines are the lines here are true energy.
No. The lines here are, if you take this data and you just the energy that was assigned here basically came from our Monte Carlo, which is the same physics as their Monte Carlo without any n particle, any n whole part. Okay. So they just simply said, we did our reconstruction of the energy correctly with the same, if they use the same model we do, they get basically the same reconstructed energy.
Okay.
Okay?
Not sure. So I guess what I'm trying to understand is
Sure.
If I'm looking at a reconstructed energy
and reconstructed energy means what in this case?
So in this case, reconstructing with the quasi-elastic assumption.
Okay, from Fermi
gas.
relativistic Fermi gas. You bet. Okay,
assumption.
that's what established those experimental energies.
Okay, then if I take my model and I add